Okay. Yeah.
All right.
Okay. So sorry for the delays with me. Okay. So hi, my name is Mehtaab, and I'll be talking about oblivious online vector balancing. And this is all joint work with Ryan Allweiss, and a graduate student at Princeton, and Yang Liu, a graduate student at Stanford. Next slide. So sort of the first classical result in discrepancy theory that I personally love is a very famous result of Spencer called 6 standard deviations suffice. So I'm going to phrase this in terms of vector balancing instead of the more familiar set connotation it's usually presented in. So you fix vectors v1 through vn on the Boolean q, so 0, 1 to the n, and you fix n such vectors. Then Spencer's theorem tells you that there's a signs epsilon1 through epsilon n, so plus minus 1 signs, so that if you look at the sign sum of these vectors, so in particular, the sum of epsilon I vi, you have that the infinity norm of this vector is bounded by 6 times square root n. Next slide. So this is equivalent to saying that given n subsets of 1 through n, one color the elements red and blue here just correspond to the signing that you assign. So every set has discrepancy on those 6 times square root n. And the original proof of Spencer was not algorithmic. In fact, he conjectured that it could not be made algorithmic. But in fact, it was made algorithmic first in work of Bunzel and then in work of Lovett and Mecca. And for further work in this direction, one particularly elegant algorithmic approach is due to Rothbose. However, Spencer's theorem is sort of a special case of a more general conjecture of Cohn-Losch. Next slide. Which says that if you fix vectors v1 through vt in Rn, such that each vector has unit, at most unit length, then you can find signings epsilon1 through epsilon. So you fix vectors v1 through vt in Rn, you can find signs epsilon1 through epsilon t, such that when you look at the sign sum, the infinity norm of that sign sum is order constant, and this should be some absolute constant independent of n and t. Unfortunately, we don't know how to resolve the Cohn-Losch conjecture, and the best known bound, next slide, is due to Banachik. So in particular, the best known bound is O of square root of log n. So in particular, if you're in n dimensions, given any number of vectors, you can find a signing so that the discrepancy is bounded by square root log n. And Banachik's original proof is also not algorithmic, similar to Spencer. However, it has been made algorithmic. It was made algorithmic in 2 works of Bunzel, Deduche, and Garg, and then Bunzel, Deduche, Garg, and Lovett. And in particular, and so, however, in this setting of the Cohn-Losch conjecture, you're given all your vectors beforehand. So you're presented with the vectors v1 through vt, and then you pick signs epsilon1 through epsilon t to minimize the discrepancy. In this talk, we'll be considering a slightly different setting, in particular the setting of online vector balancing. Next slide. So in particular, both of the previous problems we were considering were offline, while the problem we'll be considering is online. So in particular, you're given vectors v1 through vt, one at a time. So in particular, first you're presented with the vector v1, then you sort of are supposed to give it a sign epsilon1, then you're given a vector v2, you assign a sign epsilon2, and you continue going on. And the goal here is to keep sort of the infinity norm of any partial sum of vectors you have as small as possible. So in particular, we'll define the discrepancy here to be, you look at all prefixes, so the sum of epsilon j vj from j equals 1 to I, over all possible prefixes. So you can have only one vector or the first 2 vectors or however many vectors until the first over the t time steps that you've seen. And this is what we'll define as the discrepancy. So the goal of this talk is to find algorithms to minimize this discrepancy, subject to certain constraints on how the vectors are presented to you. Next slide. So just to get a feel for this, let's just walk through an example of online vector balancing. Next slide. So just scroll through a few more slides, sorry. I'll just have the whole example. Yeah, okay. So first you're given, so this is meant to come through one at a time. So first you're given the vector v1, which is -1, 1, 1, -1. Let's say you assign 1. The partial sum at that point is -1, 1, 1, -1. Then you're given a second vector, -1, -1, -1, 1. You assign the sign 1, and now you take the partial sum. It's -2, 0, 0, 0. So at this point, your L infinity norm has increased from the previous step at being at 1 to being 2. Then you're given another vector, -1, 1, 1, 1. You assign the sign -1, and you get a total partial sum of -1, -1, -1, -1. And continuing like this, we have these 5 vectors. If you pick their signs, you get, at the end, you get some vector 1, -1, -1, -1, whose L infinity norm is 1. But note that it sort of matters what signs you chose. In particular, if we were unlucky for some reason and our algorithm decided to give the signs all 1s, then the first coordinate would be -5. So you'd have an L infinity norm of 5, and that would be a poor choice. So in particular, this is what we need to avoid. We somehow need to choose the signs cleverly as we get presented the vectors, so we don't have a large L infinity norm at the end of the day. Next slide. And this may seem like an isolated problem, but there have been quite a few applications of vector balancing in sort of general. So one particularly beautiful recent work of Harsha, Spielman, and Zhang showed sort of they used the Gram-Schmidt walk in a much sharper analysis, actually. So this improving constant factors is important in the context they're thinking about. Sort of using this Gram-Schmidt walk, they were able to sort of think about designs of randomized control trials. So in particular, you have a bunch of participants and they have a bunch of associated covariates. And you want to sort of split these into 2 groups so that the 2 groups are as close to each other as possible in some sense. And this sort of turns out to be exactly a question in vector balancing. And what Harsha, Spielman, and Zhang showed is that basically, if you're able to very carefully analyze the Gram-Schmidt walk that was used by Bunsel, Dadouche, Gard, and Levett to sort of give an algorithmic version of Banachik's result on the Kolmog's conjecture, that you can use this to sort of help in the design of randomized control trials. Next slide. Similarly, within discrepancy theory, there are a bunch of classical geometric discrepancy problems, like sort of interval discrepancy, Snoddy's problem. Basically, these amount to you're given point sets. You're given a bunch of points in some space, and you want to choose signs for the points, like whether the point is red or the point is blue, so that in any given region of this space, you have very few. The number of red points you have versus the number of blue points you have is approximately the same. And this connection to online vector balancing was sort of developed in these works by Jiang, Kulkarni, Singla, and Bansal, Jiang, Singla, Singha. Next. Furthermore, they showed sort of applications of these results that they developed in online discrepancy theory to algorithms for online NV minimization. And next slide. And finally, they showed a connection between sort of vector balancing. So this is work of Gupta, Kushwami, Kumar, and Singla, where they showed this connection between sort of graph balancing. So basically, you're given an edge, and you're given an edge from some graph, and you want to orient the edge somehow so that each vertex has approximately the same number of in neighbors and out neighbors, and there's some connection to a problem known as the carpooling problem. Next slide. So up to this point, I've been a little bit vague about precisely the models of online vector balancing. So there are actually a bunch of different models, and we should I'm not going to sort of specify the different possible models. So the first model is sort of maybe the most natural model is the stochastic model. So you're given vectors v1, v2, v3, and what's secretly happening is that you're just getting a random sample from fixed distribution that you know. So in particular, you're given vi, it's just a sample from this fixed distribution pi, and then you're given it. This is a much weaker model, and sort of the strongest possible model you could imagine is sort of the adaptive model. In the adaptive model, what happens is the adversary at every time step looks at where you are and can then pick a vector to hand to you. And it turns out that this model is not so interesting in this case. In particular, the adversary just has too much power. The reason is what the adversary can do is they can look at your current partial sum, and it's some vector in Rn. What the adversary can then do is they can take a vector which is orthogonal to that vector and give you that vector. At that point, you have to add either plus or minus this vector, which is orthogonal to your current sum. So no matter what you do, your hands are tied. And it turns out that your L2 norm is going to increase. And it turns out that there's not really nothing you can do in this model, so there's sort of trivial balances, which I'll explain in the next slide. So, stay on the previous slide, sorry. And therefore, sort of the most general model you can hope to work in is the oblivious model. So here, the adversary can't change their vector choices based on the signings that you've chosen. But instead, what they can do is that they can fix vectors v1 through vt beforehand. There's no guarantee that these vectors come from some fixed distribution, but they're fixed beforehand. And they're just revealed to you one at a time. So in particular, these vectors do not change based on the randomness of your algorithm. And finally, there are a bunch of variations. One can interpolate between these. One such model is what Bunsell, Jones, Singla, and Singha call the profit model, where at every time step, you would get a vector from some distribution pi, where you know the distribution pi, but But this is still a relaxation of the oblivious model. Next slide. So this, there's a natural hierarchy in the models from most general to least general. So we're going to consider it when you're given input vectors 1 through vt, and you have the guarantee that each vector has norm at most 1, L2 norm at most 1. So in the adaptive model, sort of the example I gave where the adversary at every time step just feeds you an orthogonal vector, you can show that gives you a lower bound of square root g. And it's easy to sort of, either by greedy or rough approximately by randomized, to achieve this as an upper bound. However, in the models, the oblivious, the profit, the stochastic, and the uniform model, here by uniform I just mean you pick a point uniformly on the unit sphere and you're given it. There's a lower bound of square root. There's only a lower bound of square root log t, which is sort of exponentially better than what we're getting for the adaptive model. However, before our work, there was no such logarithmic bound known for the oblivious or the profit models. In particular, in the stochastic model, there was work of Bunsell. Next slide. There was work of Bunsell and Spencer, who did this in the uniform case, and then Bunsell, Jiang, Singha, which showed in the stochastic case you could get an upper bound of, you could, with t vectors, maintain a L infinity norm of O of n to the 3/2 times log t. So in this case, for the result, you sort of think of t as being much, much bigger than n. So sort of we don't care about the n dependence here, and they're getting some sort of logarithmic dependence in t. Next slide. And notice that one thing to note is that unlike the stochastic model, the oblivious model actually generalizes sort of very standard offline vector balancing problems. So for example, you can just look at the setup for the Kolmogorov conjecture, and you can have this, you can sort of treat this instead as an online problem. You're probably not going to solve the comotion conjecture, but you can attempt to get results sort of when your algorithm is supposed to be online instead of seeing all the vectors at the same time. Okay, next slide. And so our main result will be a logarithmic bound. So in particular, we will show given t vectors, v1 through vt in Rn, that you're able to maintain a discrepancy of log nt in the oblivious, profit, and stochastic models. I should, sorry, previous slide. I should note that there was concurrent work of Bansal, Jiang, Mecca, Singla, and Singha, which got logarithmic bounds in the stochastic model, but not the oblivious models. Next slide. So given that most of the previous work was on stochastic vector balancing, there's a couple of, let's sort of understand why this problem is slightly easier than the oblivious problem, and sort of why the techniques are sort of forced to be different. So here, recall that in the stochastic vector balancing model, the vectors vi are coming from some fixed distribution p, which you, as the person who's giving the signs, know. Next slide. And note that there's sort of a trivial way to get like square root t or square root t log t. Basically, what you can do is if you want just square root t log t, you can just sort of randomly assign sign. And even in the adaptive setting, this works. Next. Yeah. And so what you can hope to do if you're in sort of fixed issue in the stochastic setting, what you can hope to do is sort of exploit the randomness that you have at every time step to sort of improve this trivial algorithm of just randomly assigning signs. So the first case here was a result of Bunsel and Spencer, where they got square root n log t. Next two slides. And the works of Bunsel, Jiang, Mecca, Singla, and Singha, where they got these log n t to the 4 type bounds. The one thing I did want to mention is that you can actually get root log t bound, but sort of you have to pay a very bad end dependence. It's super exponential in end, and this is a result of Aru, Narayanan, Scott, and Venkatesan. So we have all these. Can you go to the next slide? And sort of broadly, all these results are sort of using some sort of potential minimization. So what they do is, this is at a very high level. There's sort of many steps in implementing this basic idea. But what they're roughly doing is you pick a sign epsilon I, so that let's say your current sum is the vector w. What you do is you pick your sign epsilon so that you minimize some potential function. In particular, one example of a potential function you choose is you look at each of the coordinates of your sum vector and you look at the cosh of it. So basically, this is some like exponentially growing function. So basically, you're picking the sign so that you don't. This is some smooth version of the algorithm where you just pick the sign to minimize the L infinity norm. Some slightly smoother version of it. Next. And sort of this can never work for the oblivious setting because in the oblivious setting, you're giving arbitrary vectors vi where the 2 norm is less than 1. And note that the algorithm I described, this potential minimizing algorithm, is actually deterministic. And this is a huge issue because if your algorithm is deterministic, then the sort of lower bound of square root t that I gave for an adaptive adversary also applies to any deterministic algorithm. So any deterministic algorithm cannot hope to do better than square root t in the oblivious model. And this is basically why previous works were sort of stuck with square root t lower bound. We're not able to do better than sort of a trivial square root t in the oblivious setting. Okay, next slide. Next. Sorry. Yeah, so now I just want to give some brief intuition about what you going to design some algorithm to handle this. The algorithm is going to be extremely simple, but so let's just give some basic intuition so that what you actually write down becomes maybe obvious in retrospect. So the first thing to note is that the algorithm actually has to just be randomized. So you need to pick these signs in a randomized way, and you need to avoid this square root t lower bound. Next. The second thing, which is sort of a big hint, is that if you look at all previous analysis of the Komos problem, sort of in the offline setting, they're all based on sub-Gaussianity. So secretly, we're talking about minimizing the L infinity norm of some vector of this partial sum. And this seems like you're sort of assigning a basis. But it turns out all the previous analysis of comotion, probably part of the reason that we're not getting a feedback conjecture yet, is that they're sort of based on sub-Gaussianity, so they're rotation invariant. So this is a big hint that if you want maybe an easier analysis, one thing you should do is that your algorithm should be rotationally invariant and should not maybe care about the L infinity norm or some smooth version of it, like we had looked previously. And finally, a very natural thing and something you can hope to do is that your algorithm should not really depend on exactly the signs you chose. Really, all that should matter is your current partial sum and the next input vector. Because sort of you made your decisions and you can't go back and change them. So exactly what decision you made are not so important, just where you are should be important. Next. And in particular, our algorithm will basically be you have a current partial sum W, you're given your next vector V, and what you're going to do is you're going to assign probabilities to plus or minus 1, sort of which signing you should choose, depending basically only on the inner product of V and W. Next slide. So this is the whole algorithm. So I'll give everybody a minute. This is actually the algorithm we'll be analyzing. So everybody should look at it. So in particular, you start at W0, which is your partial sum. So initially you're starting at the origin. And you pick some cutoff C, which is logarithmic in the two parameters n and t. There's an extra parameter delta. This is just going to control the failure probability. So it's not so important. What you're going to do is you're going to look at the inner product between your current partial sum, wi minus 1, and your next vector, vi. And based on this partial sum, you're going to assign probabilities. So if this partial sum is extremely positive, or is like very large, then you're sort of going to choose the negative sign with higher probability, because this is going to decrease the length more. And if it's very negative, then you're going to choose the positive sign, because this also decreases the length. So in particular, the probability you choose is pi is 1/2 minus the inner product over 2c. And 2c is just this cutoff parameter. And then you just update your vector. Next slide. Next slide. Yeah. And note that there's an issue here if your inner product between your current sum and your next vector is very large. So this can happen if sort of your vectors become very long and then your next vector is sort of pointing in that direction. Because in order for this probability that we define, this 1/2 minus the inner product over 2c, in order for this to be in 0, 1, you actually need this inner product to be less than c. And so and sort of the failure case of the algorithm is basically just handling this. Next. Sorry. And basically, our main theorem is that this algorithm works. So in particular, if you note, if you stare at the algorithm, it's sort of immediate that it will always have discrepancy at most log nt over delta. In particular, we sort of enforce it in this if loop. So the only question is, does this algorithm actually output anything? And so with probability 1 minus delta, it outputs. So it'll give you a valid signing with probability 1 minus delta. And one corollary of this, or it's not exactly correlated. You need to slightly modify the algorithm, but what you can also show is that sort of in the cumulus setting where there was a bound of log n, you can in linear time find a signing, which gives you a discrepancy log t times log n, or square root of log t times log n. And this sort of makes progress towards basically giving input sparse to your sort of linear time algorithms for discrepancy problems. And this is sort of a free corollary. Furthermore, you can, the various online geometric discrepancy problems that were mentioned by Bansal, Jiang, Singla, and Singha, you can sort of use just sort of use their reductions and our result, and you immediately get improvements for these problems. And finally, they're even you can even apply these, because these are oblivious algorithms. You sort of just apply them to the offline setting, and you can match up to small logarithmic factors, even the best known bounds for geometric discrepancy problems like Kuzneti's problem. Next. So the goal for the remainder of the talk is actually to basically give a complete analysis. So let's just briefly go through the steps in the analysis at a very high level. So we're considering some partial sum Wi, which is the sum of epsilon1 v1 plus all the way to epsilon I vi. And we're going to try to, because we sort of can't just analyze some potential function directly, we're sort of going to have to understand how the distribution of Wi evolves at every time step. Next. And basically what we're going to do is we're going to decompose this Wi into two parts. First, you're going to look at how the expectation of Wi plus 1 compares to the expectation of Wi. And then you're going to add in some extra term, which sort of, and so given that you have the shift in expectation, you now need to also understand what the additional variance comes from between these two steps. And sort of understanding this decomposition carefully will be sort of how we'll proceed. And using this decomposition, we'll be able to achieve the necessary concentration. But next slide. However, the key issue is you actually just need to achieve high probability bounds on the position of Wi. And next slide. And there's a couple of reasons this is sort of pretty tricky based on use sort of classical Martingale concentration techniques. The reason is, no matter, it seems very unlikely that given your algorithm, you're sort of, it seems impossible to sort of guarantee that your next vector vi will for sure not be orthogonal to your current partial sum. And in this case, that the next vector you're going to see is orthogonal to your current partial sum, there's really nothing you can do, because you know your L2 norm is going to go up, you're sort of going to move further from the origin, and sort of your L phase is going to increase. And therefore, it's very difficult to argue that some potential is decreasing pointwise. And this prevents us from using Zuma's inequality. And therefore, we have to sort of achieve a more global control over the distribution of Wi. Next slide. And sort of the key tool is actually spreading. So literally, this is a piece of bread, and we're spreading jam on this piece of bread. And much like this, we'll sort of be understanding how our distribution spreads to some other distribution. So sorry for the poor jokes, but for the actual definition of spreading, we're going to consider two random variables, x and y. So we say that a random variable y, so x and y both live in Rn. We say that x is a spread of y if there's a way of coupling them so that the expectation of y given x equals x. Next. So this might not be the most intuitive way of stating it. Sort of a completely equivalent definition is what you can show. What you can do is you can first sample x, then you know your point is somewhere here. This is your sample of x. Then you can add a mean zero random variable, which may depend on where you are, where you sampled x. You can add this mean zero random variable, and then that distribution will be y. So somehow you're going from x and you're spreading out to get y. And the the univariate notion of this definition appears in the mathematical economics literature under mean preserving spread, and it's very closely related to this other notion in mathematical economics of second order stochastic dominance. So given that we're going to have to use this tool, let's develop a few sort of easy properties of spreading. The first is linearity. So if y is a spread of x, then suppose I have some linear transform m, which is independent of x and y, then it's sort of easy to see that my is a spread of mx. Then there's transitivity. If z is a spread of y and y is a spread of x, then x is a spread of z is a spread of x. And this just follows sort of by checking the definitions. Third, and sort of most crucially, sort of the reason you define spreading is that it acts very nicely with the notion, like sort of convex functions, majorization over convex functions. So let y be a spread of x, then for any convex function phi from Rn to R, we have that the expectation of phi of x, where x is sampled from x, is less than the expectation of phi of y when y is sampled from y. And this is just actually a consequence of Jensen's inequality. What you do is you sample x and y simultaneously, and you use this coupling you have so that the expectation of y given x equals x. And then if you just use Jensen's inequality, the property of convexity follows it immediately. Next. And finally, we're sort of going to use this notion of spreading to show that our distribution at time I is spread by some appropriate Gaussian. And in order to do that, I need to say the word Gaussian somehow. And the way I'm going to get Gaussians out is, the first fact I'm going to use is that if you have any real valued random variable, which is mean zero and is bounded, so in particular it's between c and minus c, then that random variable is spread by some Gaussian. The way to see this is that any such bounded random variable is spread by some two-point distribution. In particular, it's spread by putting half mass at minus c and half mass at c, and then an easy computation get that two-point random variable spread by the appropriate Gaussian. And finally, what I'll show is that if A is less than B in the semi-definite order, then the normal variable with covariance matrix A is spread by the corresponding normal random variable with covariance matrix B. Next slide. Next slide. Yeah. So for a quick example, you're given as I said before, you're given PSD matrices A and B such that A is less than B in the dominance order, then N0A is spread by N0B. And the proof is just to note that N0B is equal to N0A plus N0B minus A, where this addition is occurring so that you first sample an N0A, and then you sample an N0B minus A, independently at random. And note that if you add these, you get an N0B. And note that this is well defined because B minus A is a positive semi-definite matrix by the condition. So in particular, if you're taking some expectation over N0B, what you can do is you can first sample N0A and then sort of add the mean zero random variable N0B minus A. Next. And note here that we have this additional special property that sort of no matter what I sampled in my first distribution, the second distribution I add actually does not depend on that first distribution. And in general, this is not true for spreading. In general, you're allowed to change the mean zero random variable you have between the samples of the first random variable. Next. So to formalize the proof, we'll need a few extra definitions. So recall that we're maintaining this partial sum Wi at every time step, and you'll be fed a vector Vi at every time step. And so Wi plus 1 will equal Wi plus either V1 plus Vi plus 1 or minus Vi plus 1, based on which sign you chose. And what we're going to say is we're going to let wi basically just be the position of the vector at time I. Note that this is actually not precisely defined, and this is sort of a little bit of an issue that we'll have to remedy momentarily. Because if the algorithm has failed, then what does it mean to be at the ith time step? Your vector is at the ith time step. If you failed like 10 steps ago, where are you? What does this even mean? So we have to actually choose a definition so that we can make sense of this. So the key idea in the case that you have not failed is to sort of note what happens to the expectation of your vector. So the expectation of the vector wi plus 1 given wi, this is just a straightforward computation, is I minus C inverse vi plus 1 transpose times wi. And the key point here is that this first matrix is strictly less than I in the positive semi-definite order. So at least in expectation, what's happening with this random walk, if you haven't failed, is that you're sort of contracting inwards, sort of with respect to the vector you're fed. And so given this sort of naturally leads to a decomposition. What you do is you write your next partial step as the expectation of where you are plus some shift. So what you can write is you can write wi plus 1 as the expectation of wi plus 1 given wi plus some random variable r of vi plus 1 wi times vi plus 1. And if you just write out what the expectation is, you get this expansion. Next slide. So now let's, if you just sort of do a computation by hand, what you find is that the following is the random variable r of wi vi plus 1 is 1 plus C inverse times wi times vi times the inner product of wi and vi plus 1 with probability pi plus 1. Pi plus 1 is this linear probability we assign to both sides. And otherwise, it's minus 1 plus C inverse times wi and vi plus 1. So note that if one of the conditions for the algorithm not to fail is that the inner product between the two vectors is at most C. So in particular, in this condition, that condition implies that R in the second two cases is bounded by 2. Sort of the way you now, this sort of gives you a very natural way of now remedying the issue of what do you do if you don't actually, if the algorithm already failed. What you then do is you just define R to be 0. So in particular, if your algorithm has sort of failed, how you're going to keep track of those points is you're just sort of going to contract them inwards based on this matrix I times C inverse vi plus 1 transpose. So basically, if you've already failed, you're just going to sort of have a what would have happened to this point. It doesn't really make sense, but it's a very convenient tool in the analysis because it allows you to have a notion of what happened to these failed points. And the key thing to note is that as long as you haven't, the algorithm hasn't failed, the construction of random variable actually gives you the true point and gives you the true position of the current sign sum. So we haven't done anything bad with respect to that. Next. And sort of, as I said before, the first thing to note is that this random variable r of wi vi plus 1, sort of by construction, it's bounded by 2. In the first case, it's 0. In the second two cases, you know that the algorithm hasn't failed. So the inner product is bounded by C, so or has absolute value bounded by C, so it's this random variable is bounded. Furthermore, sorry, can you go up for a second? Sorry. Furthermore, by construction, this is a mean 0 random variable. Basically, because it's defined as basically because of how it's defined, and you can also just check it directly. Next slide. And recall that we have this constant, which is O of log NT over delta. And the key lemma is basically that for every time step, we have that there's a corresponding Gaussian, which spreads your random variable. It's 2 pi times C I. So this is some like rotationally invariant Gaussian with whose eigenvalues are 2 pi times c, whose covariance matrix is this. And you're going to say that this random variable is a spread of wi at all time steps. Next slide. Next slide. And basically, what you show using the convexity, using the convexity relation we defined for two random variables being spread by each other, is that this guarantees a low probability that your algorithm fails. So essentially, what you do is you carefully cook up some test function phi. Basically, turns out to be the exponential of x, which is your current. You define it on Rn by taking a current vector x and some unit vector u. You look at the square of that, and you normalize it times some constant. You take the exponential of that. So some super fast growing function. And you can calculate what it is for the Gaussian I wrote. And you know that for that that upper bound is higher than what it is for your corresponding random variable, wi. And so if you just trace through the math, what you see is that at every time step, there's a probability delta over t of failing. So either your L infinity norm of your current partial sum is too large, or the next vector you see, you're not going to be able to process. But given that you haven't failed, given that you only fail with probability delta over t, over the t time steps, you're only going to fail with probability delta. And summing this basically gives the result. So the key ingredient we need is how do we actually show that at every time step, you're spread by this appropriate Gaussian. Next slide. So basically, this is just going to be a simple proof by induction. At this point, we sort of have all the machinery, and now we just need to put all the pieces together. So recall from earlier, we had this decomposition of wi plus 1 into two parts. Wi plus 1 equals the expectation of wi plus 1 given wi, plus this random variable r times vi plus 1. Okay, and if you just if you rewrite this out, you get the expression at the bottom of the page. It's wi plus 1 times this small contraction in the direction of vi plus 1 plus this small random variable. Next slide. So now we want to use that. We now want to use the fact that if you have a mean zero random variable, which is bounded by an absolute constant, then it's spread by some appropriate Gaussian. And I should briefly I didn't comment on this earlier, but why do you get this expectation, this Gaussian of variance c squared? So the reason is if you have a random variable of mean zero bounded in minus c to c, its variance can be as high as order c squared. And the easiest example to see this is you just take probability half of being minus c and probability half of being c. So this gives you a variance of order c squared. And sort of the Gaussian here is sort of the smallest, you sort of need a Gaussian of variance c squared to sort of spread this initial point. Because you can sort of show if that y spreads a random variable x, then the variance of y is higher than the variance of x. And there's this extra factor of pi over 2, but it's not so important. We can pay for that in our analysis. So recall from earlier that this additional sort of drift term r is mean zero and supported in minus 2 to 2. So applying the spreading by Gaussians, you know that it's spread by n0 2 pi, always. And notice that this is independent of wi. So this distribution you're going to spread this shifting term by is independent of where you are in space. Furthermore, by induction and sort of by this linearity property, you know that the expectation of wi plus 1 given wi is spread by the matrix ring. So if you just have wi, it's spread by n0 2 pi ci. But we also have this fact that in expectation, wi plus 1 sort of contracts in the direction of wi plus 1. So you get this n0 times, basically you have to adjust for this factor, this linear map contracting u inwards, and you get this expression. Next slide. And so now all you have to do is you just have to note that wi plus 1 equals the sum of these two random variables. And I'm hiding something here, but sort of morally, you've shown that the first thing is spread by some Gaussian, and the second part is spread by some Gaussian. So it turns out that the whole random variable is actually spread out by the independent sum of these two Gaussians. So in particular, you're spread out by this sort of ugly-looking matrix, a Gaussian with this sort of ugly-looking matrix. But it's sort of a very easy, well, not so easy, but sort of a simple computation tells you that this covariance matrix is uniformly bounded by 2 pi c times I. And that completes the proof, because we've now shown that wi plus 1 is spread by n0 2 pi ci. Note here I'm using the fact that if you have one Gaussian and another Gaussian, with the first Gaussian having a smaller covariance matrix in the PSD order than the other Gaussian, then this one spreads this one. And that's just the final fact I apply. And with that, that's actually basically the entire proof. There's some minor checking in this n0 in adding these two Gaussians, but this is sort of abstract probability and not all that interesting. Yeah. Next slide. And therefore, this algorithm is a very simple algorithm, gives you logarithmic bounds for the online Comosh problem against oblivious adversaries. And just to recall, the algorithm is very simple. What you're doing at every step is you're picking a sign epsilon I, which is a linear function of the inner product of your current vector and the next vector you get. Next. And the whole analysis was basically based on this concept of spreading between two random variables and sort of just eventually bounding the covariance in some manner, or some proxy for the covariance. And I think one very natural open question, sort of the main open question left by this work, is can you achieve Banachik's result in an online manner? There's no lower bound that would contradict this, so this is sort of the limit of what one can hope to do in the online setting. So is there a similar algorithm that gets a square root log NT bound? I suspect there is, but I really don't know how to prove anything of this form. And with that, thank you for allowing me to speak. And the paper is available on arXiv under the title Discrepancy Minimization via Self-Balancing Walk. And thank you for your attention, and happy to answer any questions.
I'm trying to unmute. I think I've eventually managed. Thank you very much, Mehtaab. People, if you write questions in the chat, or we have somebody asking for microphone access, can we give this to Zihan to ask a question? Sylvia? So Zihan was requesting microphone access. Zihan Jin. Okay.
Cool. Can you hear me?
Yep.
Yes.
Oh, thanks. So I'm just wondering, why do you choose this constant to be independent of I, but dependent of T? Why not like adjusting this C step by step?
So I'm pretty sure you can do this, I think. The issue is if you do this step by step, it sort of doesn't help. But the point is basically the choice you would make on the last like or T over 2 vectors sort of determines everything. And you're going to make the same choice up to a constant. You might be able to improve constant vectors, but we were also not particularly careful in optimizing that. But yeah.
Oh, thanks.
Okay, so everybody, you're still very welcome to write questions in the chat or to raise your hand as Zihan did. Thanks for the question. Maybe I'll ask one in the meantime. So, or a couple. So, firstly, like, could you carry out this analysis sort of by directly fiddling with some exponentials and some expectations without the spreading concept?
Yeah. So there's there's a little way of seeing what's happening in a sort of dual form, which explains this question very nicely. The point is, if one random variable is a spread of another random variable, I said this convexity condition. It's equivalent to sort of saying that you can check that spreading is equivalent, that you have this property for all convex functions simultaneously. So there's sort of it's actually a two-way condition. So in this way, basically, we're inducting on the set of all convex functions simultaneously. What you can do is, as you said, basically run this analysis on the set of exponential functions, like exponential decay functions simultaneously. What ends up happening is that let's say you want to bound the exponential moment in some direction. What's going to happen is you're going to tilt this direction and use the previous step in that tilted direction. Use that bound and then induct. So it does work. It ends up being equivalent. And I think you might even get a slightly better concept, but the issue is it's very strict. It's the same induction, but the reason it ends up being strange is you're inducting on all directions simultaneously. And this also tells you why the Zuma is failing, because you're not looking at the same direction at all times. You're sort of changing direction as you proceed. But yeah, you can just do the analysis that way.
Okay, yes, very interesting. We had a question in the chat. Is there a way to avoid choosing delta in advance?
Not with the current algorithm. There are modifications of the algorithm that I believe work, but I have no idea how to prove anything about that wouldn't have this property. The analysis here actually does require this. This cutoff, basically what I'm using very strongly is that this function I'm choosing is sort of a linear function of both the inputs, both your current vector and the next vector you're fed. And given that, that sort of forces this this sort of cutoff point at C, which is in some sense artificial, but yeah. So I don't know a way of doing that in particular.
So what's the different algorithm that you can't analyze?
Oh, I mean, so I think basically anything should give root log NP. Basically, literally, instead of this cutoff being like some log, if you make it 4, and if you're outside this range, make it deterministic, I'm pretty sure it works. I just have no idea how to analyze it. I tried for a few months. We'll try again, but no. Yeah, I have no idea how to analyze
it. Yes. Oh, we have another question. From Julia, can you get discrepancy with respect to other norms?
So basically, yes. You need to. It depends basically on the Gaussian volume of the norm, the corresponding convex body. Because what you're showing at every time step is that you're spread by some Gaussian. So essentially, this amounts to Gaussian volume computation. This is, if you're familiar with Banachik's theorem, you can get some version of Banachik's theorem. It's not going to get 5. It's some like root log NP times K, but it's something like, you can get something like that. And there's sort of an easy consequence of this Gaussian spreading fact. You can also, you don't actually need Gaussian spreading here. I'm pretty sure you just need sub-Gaussianity of the final distribution, which follows from the exponential moments as well. Yeah.
Thank you. Maybe in the chat. Oh, Julia saying thanks. So maybe I'll ask sort of relatedly, you were saying you think maybe like you can't get all the way to the Kolmogorov conjecture with rotation invariant algorithms. I guess that's reasonable. Do you have do you think there might be a lower bound of some sort?
So all the current analyses of Kolmogorov can be sort of said in the following. This is not really true of Banachik's work, but it's more true of what this Graham-Schmidt-Walk paper does. What they show is that at the end of time, this distribution is sub-Gaussian with their thing. And then they just use what the Gaussian volume of a box is. I have no idea how. Like the point is like if your algorithm is rotation invariant, I don't see how you can guarantee anything stronger than that. That's I think the issue. It's not a question of sub-Gaussianity. Also, all these things succeed with high probability. You might have the issue, something like a Caddison-Singer type issue, where you're not going to get a high probability type bounce. Caddison-Singer is very hard for a reason. That's why, yeah.
And then following up to that, like, do you think that this like spreading, is it very important that you're using Gaussians, or like could you make use of this like in other contexts, presumably?
So it's always nice to do with Gaussians. I mean, I'm pretty sure Yang has claimed this to me a few times, and I'm pretty sure it's true. What you can do is you can instead spread to like an interval at every time step, and then use some like properties of log concave distributions. This does work, but it's not the easiest thing to write down. But yeah, so what really matters is that you have the correct tail bounce every time step, nothing more than that.
Yeah. Okay, I'm not sure if we have any more questions, so maybe let's thank Mehtaab again and say that like everybody's very welcome to go to the talk session afterwards. It's